Okay, guys, it's Question Friday. What do we need some clarification on? Some of these I'm going to actually make a second video, probably two more this morning, to explain more in detail some of the processes that may require me to write things out for you. So, this won't be the only video. Of course, the others are optional, but I highly recommend them because someone had a question about it. So, strong and weak acids or bases. There are 7 strong acids. You'll need to memorize them. I've given them to you before. And it's just a list of things that completely dissociate in water. And there are also, conveniently enough, 7 strong bases. The strong bases come from groups 1 and 2 on the periodic table. All the group 1 hydroxides are strong. Group 2, however, have a few that have solubility issues. They don't dissolve very well in water, and so they are not considered strong because it is an equilibrium. Everything else that you hear about or see, if it is not on that list of 7 strong or 7 weak acids, then you are, or 7 strong or 7 strong acids or bases, then you will treat them as weak. You will then have to do rice. So the strong completely disassociate, the weak do not. So you're going to do rice, and I'm going to do a video on that. And if you're asked to rank them, typically you'll be asked to do that one of two ways, either based on what you see in their structure, or you'll be given KAs or KBs. And the larger the KA or the KB, the stronger. And so you just compare those. My advice with those as well is that you have to have them in the same exponent to kind of compare them, because those negative exponents get me every time. So I would suggest you get them into the same number for the exponent. So what about sulfuric acid and calcium hydroxide? These are not one-to-one. They don't have just one hydrogen or one hydroxide. So when we have an acid, we have to do those protons one at a time, because removing one of the protons affects how the second one's going to act. So the first one in sulfuric acid, for instance, and you take off that first hydrogen ion, you get that's a complete dissociation. In fact, that shouldn't be a double arrow, that should be a one arrow, because it has such a high Ka that it completely dissociates. The second one, however, now that bond between hydrogen and oxygen in hydrogen sulfate is much stronger, because we've already put a negative charge on it, and it doesn't really want to go to a 2 negative charge, so it makes that second hydrogen much harder to remove, and you can see that it has a Ka then that is somewhat small. So acids, the protons you deal with one at a time. You write as many equilibrium statements as possible. And so if you look at this first equilibrium, we have the 2 hydrogens on SO4, and we've removed one. Now we're going to take that product that started from our acid. It is still an acid, so we're going to bring it over to the next line and start with that one. And now we're going to remove the second hydrogen from it. And we will then get a SO4 minus. So bases, however, are much more simple. They go all at once. If it's strong, all the hydroxides fall off together. So there's only one equilibrium statement, and you're just going to use stoichiometry to balance out your hydroxides. And so since calcium hydroxide has a 2 outside the parentheses for the OH, you take them both off at once. And so then if I had a concentration of calcium hydroxide that was like 1 molar, then when it disassociates, I would have 2 moles of hydroxide for every 1 mole of calcium hydroxide. So my hydroxide ion concentration would be 2 molar, not 1 molar. So Rice is one of those videos I'm going to make and walk through pretty slowly with you, so please watch for that one. I will put it up onto the playlist on probably the problem videos. So, someone asked me about acids and base conjugate pairs. I'm going to work this problem, these three, in a video, going through it very step by step. And so here's the second one I plan on doing this morning. You're basically still just applying those definitions of, is this species, whether it's on the reactant side or the product side, able to act as an acid or a base? You apply that definition and that tells you what it is. If it's on the product side, it's a conjugate of that. If it's on the reactant side, it's just that. So if it has, like HBr, has a hydrogen to donate, so that makes it a Lewis acid, hydrogen ion donor. H3O plus, that has a hydrogen ion to donate, so that will be a conjugate acid. Because it's on the product side, it's conjugate. So, buffers. We will cover those shortly. We have not yet covered them. That's coming up, I think, either in the next lecture video or the one after that, depending on how long it takes me. Acid-base strength based on structure. This I have talked about, and in fact, I've just pulled those slides into this presentation. These typically are applying to things that are not these are typically organic acids and bases. They typically can have an OH or a nitrogen in them, and we can decide based on that whether they are acids or bases. And how do you decide which is stronger? So, if they have one or more OH groups, we're going to refer to the bond between the oxygen and the main chain as bond A, and then the bond between hydrogen and oxygen is bond B. So, these can be acidic, basic, or amphiprotic, or amphoteric. And it would depend on element E, the rest of that chain. So, if E is low in electronegativity, then bond A is polar or ionic. This would be something like if that was a sodium ion or an aluminum ion. And that means that we can remove OHs from those compounds. Since we can remove OHs, that's one of our Bronsted-Lowry base definitions, are actually Arrhenius, and so this compound would be basic. So if E is a metal, then it is going to be a metal hydroxide, which will be basic. If E is high in electronegativity, which means it is a nonmetal, something like sulfur, phosphorus. Now the bond between E and O, or bond A, is covalent. You cannot break it easily. Therefore, the bond between hydrogen and oxygen, bond B, is polarized. It is weaker, and therefore we can remove a hydrogen ion, creating an O minus and an H plus. So this compound would be acidic. So now we can decide whether something is an acid or base based on the identity of E. If it's a metal, it'll be a base. If it's a nonmetal, it'll be an acid. Now, if E is in between that, then that will be it will be amphiprotic, which means it could be an acid or a base. It will depend on what it's with. And so if it's in the presence of an acid, it will act as a base. If it's in the presence of a base, it'll act as an acid. So hopefully that is helpful for you. We will talk some more about predicting acid strengths based on the other things attached to E at another time. Thanks for watching.